Hello, our lesson for today is AC analysis of a BJT or bipolar junction transistor voltage divider bias using RE model. Our objective is to develop an RE model and solve for the values of the input impedance ZI and the voltage gain AV of a voltage divider bias BJT circuit. Let us consider this circuit. We have VCC is equals to 22 volts, RB1 equals to 56 kilo ohms, RC 10 kilo ohms, RB2 is 5.6 kilo ohms, and RE equals to 1.5 kilo ohms. This is our input voltage and our output voltage with polarity shown, and we are looking at this point our ZI, and at this point our ZO, or the output impedance and input impedance. The beta of our transistor is equals to 90. Notice that RE is bypassed by the bypass capacitor CB, and we have two coupling capacitors CC1 and CC2. The RE equivalent model, approximate model, is shown here. We have VI, our input current. This is the base, the emitter of our transistor. This is our collector side, and we have RBB, which is just the parallel combination of RB1 and RB2. The approximate resistance from base to emitter is beta RE. This is our current source, beta IB and RC. So, to find VBB, which is our Thevenin's voltage at the base, we are going to use the equation VBB is equals to RB2 VCC divided by RB1 plus RB2. This is by using the voltage division theorem, and VBB is our voltage at the base. So VCC, total voltage source, multiplied by RB2 divided by the sum of RB1 and RB2. So if we substitute the value of RB2, which is 5.6 kilo ohms, multiplied by 22 volts for our VCC, divided by the sum of RB1, which is 5 or RB1 56 kilo ohms plus RB2 5.6 kilo ohms, we could obtain the value for our VBB to be equal to 2 volts. Okay, for our RBB, okay, let's just put the value here for VBB is equals to 2 volts. For our RBB, it is simply equals to the parallel combination of RB1 and RB2. RB1 in parallel with RB2. And by using the formula for parallel resistances, two parallel resistances, we can use the product over sum formula, which is RB1 multiplied by RB2 divided by the sum RB1 plus RB2. And if we substitute the values for RB1 and RB2, you get 56 kilo ohms multiplied by 5.6 kilo ohms all over 56 kilo ohms plus 5.6 kilo ohms, and RBB has a value of 5.09 kilo ohms. So our RBB is equals to 5.09 kilo ohms. Now we need to solve IB, or the base current, in order to solve for IC and IE, and that values is needed, or IE is needed, in order to solve for RE, our AC resistance. So from this diagram, this is our Thevenin's equivalent circuit. At the base, we have VBB in series with RBB, and this is our base emitter junction with a voltage VBE, and VBE is equals to 0.7 for silicon transistors, and RE, or the emitter resistor. The current that flows here is IE, and the current that flows through RBB is IB. So if we set up our KVL, or our Kirchhoff's voltage law around this loop, we have VBB minus IB RBB minus VBE minus IERE equals to 0. But IE is equals to IB plus IC, and we know IC is equals to beta IB, so we have IE to be equals to IB plus beta IB, and if we factor out IB, we have IE is equals to IB times 1 plus beta, or simply IE is equals to beta plus 1 IB. Okay, such that our VBB, or our equation becomes BBB minus IB RBB minus BBE minus this value beta plus 1 IB multiplied by RE equals to 0. And by using algebraic techniques, we can find IB to be equal to BBB minus BBE divided by RBB plus beta plus 1 RE. So this is our formula for IB. And if we substitute our VBB, VBE, RBB, and beta, and also RE, we can find the numerical value for IB. So IB is equals to 2 our VBB minus BBE, which is 0.7, divided by 5.09 kilo ohms for RBB plus 90 plus 1 beta plus 1 multiplied by RE, which is 1.5 kilo ohms. And using our calculator, we can find IB to be equal to 9.18 microamperes. So IB is equals to 9.18 microamperes. Now we need to have the values of IB in order to solve for IC. IC is just equal to beta IB, and since beta is equals to 90, substituting that value, and also IB 9.18 microamperes, we can find IC, which is at this point we can approximate IC to be equal to IE, and IC approximately equal to IE. Solving this, we can get the value of 0.826 milliamperes. We have the formula RE, or the AC resistance, to be equal to 26 millivolt divided by IE, and if we compute RE, we have 26 divided by 0.826 millivolts and milliamperes. That's the RE is simply equals to 31.5. RE is equals to 31.5 ohms approximately. So RE is equals to 31.5 ohms. Okay. I have here a derivation of this AC resistance RE, and if you would like to know the derivation, let me present it to you. We will begin our derivation from the Shockley equation for the base emitter PN junction. IE, it states here, IE is equals to IR multiplied by the quantity E raised to the power VQ over KT minus 1. And IE is the total forward current across the base emitter junction. This is our IE. The reverse saturation current is IR. The voltage across the depletion layer is V. And the charge on an electron is Q. Boltzmann constant is K. And the absolute temperature is T. At ambient temperature, we have the value for the charge on an electron to be equal to 1.602 times 10 to the negative 19 coulomb, and the Boltzmann constant is 1.38 times 10 to the negative 23 units meter squared, kilogram per second squared, degrees Kelvin. And the temperature at ambient temperature is, we will use 298.15 degrees Kelvin, such that if we substitute these values, we can get the ratio Q over KT to be approximately equals to 40. Now, the AC resistance RE of the base emitter junction can be expressed as dV over DIE. So, where does that expression come from? From this formula, IE is equals to IR multiplied by the quantity E raised to the power VQ over KT minus 1. And if we substitute the value Q over KT to be approximately equals to 40, we can have our equation for IE to be equal to IR times E raised to V40 minus 1, and simplifying, we have IE is equals to IR by distributive property E raised to V40 minus IR, or simply IR E raised to 40 or V40 is equal to IE plus IR. If we differentiate IE with respect to V, we have derivative of IE with respect to V. We can have the derivative of this function with respect to V, IR E raised to, say, 40V, that just interchange the order, minus IR. And This reduces to taking the derivative of the exponential function IR multiplied by 40 times e raised to 40v minus 0, because the derivative of IR as a constant is equals to 0, and the derivative of the function e raised to a to the u is equals to a e to the u du. Such that the derivative of IE with respect to V is just simply equals to 40 times IR E raised to 40V. Since IR raised multiplied by E raised to B40 is equals to IE plus IR, you can simplify this as 40 times the quantity IE plus IR. This is our dIE over dV. Now, going back to what I've said before, the AC resistance RE of the base emitter junction can be expressed as dV over dIE. And if we assume IR is much smaller than IE, from dIE over dV is equals to 40 multiplied by the quantity IE plus IR. Since IR is much smaller than IE, we can have 40 multiplied by just IE. Approximately equals to 40 IE. So therefore RE is equals to dV over dIE, which is just the reciprocal of this term. So this is equals to 1 over dIE over dV. And if we substitute the value of 40 multiplied by IE, this is equals to 1 over 40 IE. And this leads us to 1 over 40 multiplied by 1 over IE. So therefore RE now becomes, since 1 over 40 is equals to 0.025, if we calculate the value of 1 over 40, that is equals to 0.025, RE now is 0.025 divided by IE. Okay? So the unit is volts per ampere or in ohms. Unit is in ohms. And solving for RE, if we substitute the value of IE, this is equivalent to approximately equals to IC. Previously we have solved RE to be equal to 31.5 ohms. Okay, so let's go back to our main problem, solving for the input impedance and the voltage gain. Now let's go to solving for the input impedance ZI. From this circuit, ZI is just the parallel combination of RBB and beta RE. So I have prepared here the solution. ZI is the parallel combination of RBB and beta RE from this circuit. So substituting values for RBB, which is equals to 5.09 kilo ohms multiplied by beta RE, which is 31.5 ohms, divided by RBB, 5.09 kilo ohms plus 90 multiplied by 31.5 ohms. We can get ZI, or the input impedance, to be equal to 1.821 kilo ohms. Now this formula came from our parallel resistance formula, product over sum. So ZI is equal to 1.821 kilo ohms. For the voltage gain AV, our formula is negative VO over VI. And if we consider this circuit, VO is the product of IO multiplied by RC, since IO is the same as beta IB. So VO is simply beta IB multiplied by RC. And VI is the voltage across base and emitter, which is simply the current IB multiplied by beta RE. VI is beta RE multiplied by IB. And if we substitute VO over VI in our formula, AV therefore is equals to negative beta IB multiplied by RC over beta RE multiplied by IB. And it is obvious that beta cancels out and also IB, such that the voltage gain AB reduces to simply negative of RC divided by RE. And since RC is equals to 10 kilo ohms from our original circuit, RC is 10 kilo ohms. So therefore our voltage gain is simply equal to negative 307.